Welcome back to my YouTube channel, Statistics for Beginners. Today we'll be discussing about this topic, design of experiments, which is an important topic in statistics, and there will be a series of videos which will mainly focus on the syllabus that is for the optional paper of statistics for the upcoming exam, Inspector of Statistics, conducted by APSC. Now let's begin with the simple introduction why we need to design the experiments. These are some of the books suggested. One book is by Cochran and Cox, Experimental Designs, Montgomery, Design and Analysis of Experiments, Gupta and Kapoor, Fundamental of Applied Statistics. Our first slide is all about why we need this designing of experiments. Experimentation provides us what is called experimental data in contrast to observational data, which are represented by observations on the elementary units of a population or of a sample. The observational data cannot be changed or modified by any attempt during the course of the observation. It is often difficult to assign cause and effect by studying observational data. For establishment of causal relationship, experimental data should be used. So if we differentiate data into two types, that is observational data and experimental data can be modified, can be well planned so that the data could be more precise. But observational data, we cannot modify any data. We just have to observe and we can record such data. In other words, experimental data are the results from logically designed experiments which provide evidence for or against theories of cause and effect. So mostly to study cause and effect relationship, we cannot use the observational data, but we have to go for experimental data. The observations obtained from a carefully planned and well-designed experiments in advance give entirely valid inferences. This is also one of the important point. The certainty of the conclusions so drawn regarding the acceptance or rejection of the null hypothesis is given only in terms of probability. So, if my viewers have observed the ANOVA one-way and two-way video, there also we have been testing using the test of hypothesis for more than one, more than two means. Our null hypothesis was they are uh, equal, and our alternative was they are significantly different. In design of experiment also we compare certain treatments that they are equal and either they are significantly different or they are equal. So in coming slides we'll be discussing about the treatments. So all this conclusion in statistics that is a part of test of significance is done in terms of probability. Now, it is a bookish definition here in the slide. It has been added that the design of experiments may be defined as the logical construction of the experiment in which the degree of uncertainty with which the inference is drawn may be well defined. Now, some of the characteristics, how we can know, how we came to know that it is a good experimental design. So, first, provide unbiased estimates of the factor effects and associated uncertainties, enables the experimenter to detect important differences, include plan for analysis and reporting of the results, give results that are easy to interpret, permit conclusions that have wide validity, shows the direction of better results. It is as simple as possible. So these are some of the points, and there are many other points how a design could be a good experimental design. We are moving forward to some of the terminologies that will be discussed in this slide about that are involved in this design of experiments. First is the experiment. When we talk about experiment, we have two types of experiment. One is absolute and one is comparative. An experiment is a device or means of getting an answer to the problem under consideration. Experiments can be classified into two categories, absolute and comparative. So, by our previous slides, we come to know that in design of experiments, it is a comparative class of experiments, not absolute. Treatments, as I was talking about treatments, various objects of comparison in a comparative experiments are termed as treatments. So mostly some of the agricultural treatments in the example it has been included in the field experimentation. Different fertilizers or different varieties of crops or different methods of cultivations are the treatments. Now our third terminology is experimental unit. The smallest division of the experimental material to which we apply the treatments and on which we make observations on the variable under study is termed as experimental unit. Example in field experimentation, the plot of land is the experimental unit, and so on. So, experimental unit is, we can simply understand, it is that unit of the experiment on which we will apply the treatment of interest. Now, blocks, this is also one of the important terminology in design experiment. In agriculture experiment, most of the times we divide the whole experimental unit into relatively homogeneous subgroups or strata. These strata, which are more uniform among themselves than the field as a whole, are known as blocks. So, blocking is also one of the part uh, to control the variation that will be arising in designing the experiment. So, it will be discussed in some of the related designs, and one of the video I have in my YouTube channel, that is CRD. The blocking is not done in such kind of design, but after CRD, randomized block design, or LSD, the blocking will be done. Yield, the measurement of the variable under study on different experimental unit, example plots, are termed as. So when we apply certain kind of treatments to the experimental unit, its outcome or yield will be recorded. So yields is denoted with such terminology. Now it is the most important terminology of design experiment, that is experimental error. The variation from plot to plot, which is due to random or chance or non-assignable factors beyond human control, is known as experimental error. The error includes all type of extraneous variation due to the inherent variability in the experimental material, lack of uniformity in the methodology, lack of representative sample. So these are some of the sources we can say how an experimental error could be arise. But mostly in field experiments, in agriculture field experiments, design experiment is due to uh, variation due to its fertility gradient of the soil, and all other factors are also involved, but mostly fertility gradient of soil has been controlled in, and it is considered as one of the important sources of experimental error. Now, these all design that are been these all experiments that are been designed with the help to increase some kind of precision of the experimental design. So to plan such design, certain principle has been developed by our father of modern statistic, Ronald A. Fisher. So we'll be discussing them now. The purpose of designing an experiment is to increase the precision. The precision of an experimental design is increased by reducing experimental error. For reducing the experimental error, we adopt certain techniques. These techniques form the basic principle of experimental design. The basic principle of experimental designs are replication, randomization, and local control. So these are the three basic principles of experimental designs. Now, how we will be knowing that how much precise the any experimental design is after being that experiment has been designed. Now it is the formula, and here uh, it has also been given as 1 by variance of sample mean equals to small r by sigma square. Each measurement made in an experiment contributes a certain quantity of information pertinent to the population. The amount of information per variation is measured as the reciprocal of the error variance. It is also known as precision of the experiment. Thus, for any experiment replicated small r times, the precision is given by this. So, the replication, that principle, is inversely proportional to the precision. If we is directly proportional to the precision, or inversely proportional to with the help of this formula we can understand, because um, precision is inversely proportional to the variance. If the design have less variance, then the precision will be more, and if the design has less precision, the variance will be more. So precision and replications are directly related. That will be seen in the upcoming slides when we discuss about replication. And sigma square is denoted as error variance per unit. When the information from an experiment is more, we say that the precision of the experiment is more. Now, how will we knowing that either the design are efficient or not? So anything, when we have to calculate the efficiency of something, we have to compare with a standard uh, observation. So here also we will be comparing efficiency among the two design. So consider the designs D1 and D2 with error variances per unit, sigma 1 square and sigma 2 square replication, small r1 and small r2 respectively. Then the ratio, and also we can say the formula of efficiency is capital E equals to R1 by sigma 1 square divided by R2 by sigma 2 square, is termed as efficiency of the design D1 with respect to D2. As I have already said, here the efficiency of the D1 has been calculated with respect to D2. So if the value of the efficiency comes out to be 1, then we'll be saying that both are equally efficient. If it is greater than 1 or less than 1, then the design is said to be more or less efficient than D2. Now, the first principle that will be discussed, that is the replication. Replication means repeated application of the treatments under investigation is known as replication. If the treatment is applied once, we have no means of knowing about the variation in the results of a treatment. Only when we repeat the application of the treatment several times, we can estimate the experimental error. The experimental error will help to determine whether observed differences between treatment means are real or not. So this main uh, objective of this design experiment is to compare the treatments and for actual comparison, actual difference to come out, we have to use this principle of replication. Because if we apply only one treatment to one plot of land or one experimental unit, we cannot get the actual difference. So we have to replicate it as many times as required to get the actual difference between the treatments. So how many number of replication is required for a such kind of design? Here a formula has been developed, that is small r equals to 2t square multiplied into s square divided by d square. The number of replication required in an experimental design depends on the factors like cost, variability of the test material, etc. The formula is given as this, where this t table is the level of significance that has been acquired from a t table, and small d is the difference between means of two treatments, small s is the error variance, small r is the number of replication. Now we are moving forward. Another one is randomization, another principle, second principle. When all the treatments have equal chance of being allocated to different experimental unit, it is known as randomization. The usefulness of this technique can be explained by an example. Suppose that a piece of land is chosen and divided into two halves, each having a number of plots. In one half, one variety of cotton is sown, and in the other, a second variety is sown. Then the experiment may not lead to valid conclusions, since the soil fertility may be different into two halves. Hence, our conclusion about the experimental results will be valid only when both the varieties or treatments are subjected to all types of soil fertility equally. In the absence of a prior and exact knowledge of fertility variation in the field, we cannot allot the treatments to specific plots deliberately. Therefore, we have to adopt randomization technique. So, randomization technique is very much important principle in design experiment, as well as our all statistical theory. Before applying any kind of test, we require a random sample. So here also, since we are using statistical test only, therefore we require a randomization principle to be followed. Now the another side is about size and shape of the experimental unit. How will we deciding that what are the size and shape of the experimental unit? The size and shape of the experimental unit will affect the accuracy of the experimental results. In agriculture experiments, comparative studies on plot size have been carried out and found that an increase in plot size increases the precision of a single plot yield. This results in decrease in the variability of an experiment. However, an increase in the plot size results in an enlarged block, and variability within the block may be increased. To maintain a balance between these two opposite tendencies, a plot with optimum size is to be selected for this purpose. So, they also play a role in increasing the precision of the experiments. These experimental units that will be um, used while designing these experiments should be a proper shape and proper size. So to obtain the optimum shape and size of the plot, we have three methods. We have two methods: maximum curvature method and Fairfield-Smith's variance law. So, and other factors are also involved in determining the shape and size of the plot, like kind of crop, available land area, number of treatments, type of machinery, etc. So this was a short video regarding experimental design. Some principles and some terminology has been discussed. So in my upcoming videos I'll be discussing more about experimental design. Thank you all.